Hi everyone, this is PrachiGupta. Welcome to the new collab session. So in this one, this will be an advanced guide on tensorflows and keras. Today we are going deep into custom layers, advanced architectures, and building operations from ground up. Our motto for this session is to understand the framework and build it from scratch. We'll start with the setup. We are importing TensorFlow, Keras 3 and the core visualization tools. So let's import them. I'll just run it. These are imported. Now we are also enabling the GPU memory growth so that the framework doesn't seize all available hardware resources at once. We are setting a random seed of 42 to ensure every custom gradient we calculate is reproducible. So here we are doing that. We are defining this seed value and we are also doing this GPU memory growth settings. So once that is done, we will move ahead. We'll move ahead to advanced gradient tab pattern. In part 1 we moved beyond the basic in starting we moved beyond the basic back propagation to explore the nested gradient tabs. So let's see, here we are doing advanced uh, gradient tab patterns. So here we can see in this part we will use the gradient tab for simple gradients, and now we will do nested tabs. We will do Jacobian and Hessian's computation. We will do gradient custom gradients and the gradient clipping. So let's see how we can do nested tabs higher order derivatives. Suppose we have the first, second, and third derivative like this: x to the power 4. Its first derivative will be 4x to the power 3. Its second derivative will be 12x to the power 3, and its third derivative will be 24x. So we are defining a variable here, and then we are going to do three derivatives gradient step here, and then we can see the output. Let's run it. So we can see fx is equals to x to the power 4. Then we can see fx, the first derivative, second derivative, and the third derivative. So this is how we operate like nested derivatives. Now we will see the Jacobian's computation. So next we'll see compute the Jacobian's computation and Hessian matrices. Jacobian represent all the first order partial derivative of a vector, while Hessian represent the second order partial derivative of a scalar function. So let's run it. First we will do the Jacobian. So it will be the first order derivative of the function. So for a function Rn gives Rm, the Jacobian's J is m cross n, where J of I is df of I by dx of j. So we have defined x is equals to a vector, and then we are doing the gradient tape where we have defined the vector function, and then we are doing it over a stack, and then we are computing the full Jacobian function, and then we are printing the output. So if I run it over there, we can see the f, we can see the x, we can see the fx, and in the Jacobians we are returning 3 cross 3 matrix, which is computed like this. So moving forward to the Hessian computation. So Hessian is a matrix of second order partial derivative. We can see it is defined as h of ij is equals to d to the power 2f and dx I and dxj. The x is we have defined the x variable, and then we are doing gradient tape with two level derivative. So it is because it is second order partial derivative, so we are doing two order derivative, and we have defined the function here, and we are doing the calculating the gradient, and then we are calculating Hessian as tape to Jacobian gradient x. So this is how we calculate it, and we are printing the results. This is the gradient and this is the expected, both are same, and this is the Hessian and this is the expected, both are same. So let's move to custom gradients. Sometimes we need custom gradients for non-differentiable operations. So let's see how we can do custom gradients. We can use at the rate tf dot we can use tf dot custom gradient to define the custom gradients. So we will define a clip gradient norm function in which we will do forward for identity function and backward pass for clip gradient norm. So we are defining a gradient function where we will be defining the norm and then the clipped function, and then we will return the clip, that is the we will only return the gradient for x, and then we will test the custom gradient. We will create one variable, and then we will call the gradient function, and then we will from here we will call the clip gradient norm, and the gradient would be 1 1, but we pass 3 4. So let's see, we will manually set the upstream gradient to 3 4, and then we will run it. So let's see how it comes. So we have set input as 3 4 and the gradient clip to norm to 1, and this is the gradient value, and the gradient norm will be 1. So now moving to the straight through estimator. So straight through estimator allows us to train through discrete operations like rounding by passing the gradient through unchanged. So here we can see the straight through estimator is used for binary discrete operation that are non-differentiable and quantization in neural network. So we can do this by tf dot gradient custom gradient function. We will do the forward pass by roundest to the near integer, and then the backward pass by doing the pass gradient through unchanged identity. So here we will define the gradient function where we will return the straight through gradient, and in the straight through gradient we will return the rounded off value of the gradient. So we are also defining straight through sign where we will do the forward sign and then return the hard 10h value. So we are defining the gradient function where we will pass it, and the gradient is 1, otherwise on this condition, and then we will return the sign of the vector and then gradient. So we will call the test. Now we will define a variable, and then we will with the gradient function we will call this through round to print the result, and then we will print the result. Let me just run it. So this is the input, this is the rounded in output, and this is the gradient. The round is non-differentiable, but we can still train. So moving forward to, we will wrap up our part 1 with a gradient accumulation. This pattern allows us to simulate a very large batch on limited GPU memory by accumulating gradients over a several mini batches before applying a single weight update. So let's see how does it works. We have defined a training accumulation function. We will train with gradient accumulation with effective batch size by calculating by this formula. For each step in range we will define start, end, and then we will slice the objects. We will define the gradient function where we will call the model, and then we'll reduce the mean for prediction and loss. We will calculate the prediction and loss, and then we will compute the gradients. Once the gradients are calculated, we will accumulate them over the step, and then we will apply the optimizer function, and then we will return the loss. So this is how we calculate the gradient accumulation. Now we will move towards building neural network primitives by hand. So how do we build primitive neural networks? So convolution from scratch, we will see convolution to 2D naive. We have defined this function. It takes this parameters where input tensor is input a tensor, and kernel is the one more tensor, and these two are the integers. So we are defining a batch size, we are defining in-edge, in-w, we are defining kh and kw from input tensor and kernels, and then we are defining the out channels also. If padding is there, we are doing it, otherwise we will move to out h and out w calculation. We'll calculate this, and then we will create a tensor array of this output. Once we have all these things, we'll loop through the data, and then we will calculate the convolve where the sum over h w in channels, and then we will check the batch and the kernel. So here we are doing the and sum function with patch and the kernel. This is our function that we are doing here. and then we will write the output, and we will stack the output, and then we will do the transpose, and then we will return the output, and then we will test our implementation here. Let's see, let's run it. We can see this was our input shape, this is our kernel shape, and this is our output shape, and it is matching with the convolution manual automatic function. Let's move to the next, that is max pooling from scratch. So we do max pooling manually, extracting windows and taking the maximum values. So then we will verify our math against the built-in max pool to prove that implementation is correct. So we will implement our max pool function here, and then we will also calculate the max pool function directly with the formula tf.nn max pool, and then we will see that this is our pool and this is tf pool, and we will compare both our pool and tf pool and see if the results are same or not. So if I run it, this is our input, this is our output, and we can see both are matching. So our defined max pool is matching with the inbuilt max pool function. So this is how we do it. Then we will do the batch normalization from scratch. The normalization is a key to stable training, builds batches normalization from scratch and highlight the critical shift in logic between training and inferences. This implements this batch normalization from scratch. So let's see how we do it. We'll define during training and what we have to do the during inference. So let's see, we have defined this init function where we're defining our learning parameters. We are defining our running means and statistics, basically running mean and running variance. And then we will define a call function where we will compute the batch statistics, and then we will update the running statistics. uh, then we will normalize it and scale and shift our gamma, scale shift our output, and then we will call this then we have this train variable function for training, and then we will test our batch norm from scratch function with passing the features, and then we will create a batch of 8,4 features, and then we will train and evaluate our data, and let's print the output and see. So we can see the input shape, the input mean per feature, we can see the input is standard deviation per feature, and then we can see the training mean, training standard deviation. And if you see after batch norm, each feature has approx 0 mean and 1 standard deviation. So that's what we were trying to convey. Now the next is a layer normalization from scratch. So uh, layer normalization is in which normalizes across features and then the batch, and rather than a batch. So basically layer normalization is a normalization which normalizes across the feature rather than a batch. A standard in the transformer model is needed. So we work in batches, we work in across the features rather than the batches. Again we will define one class for layer function. Then we have this learnable parameters in the init function. We have this call function where we will do the statistics, will normalize, then we will scale shift, then we will test the data from a random tensor, and we will see the output. We can set the input, we can see the input and output, the output mean and standard deviation, and we can see the key difference between them is this is across the feature and layer norm is across the sample. Dropout from scratch. So finally we have built inverted dropout. The inverted part is crucial. We scale the surviving neurons by 1 divided by 1 minus rate during the training so that the expected value of data remains same during the testing. So during the training we'll do that. So let's create this function where if not training rate is equals to 0, we will return x. If it's training, then we will create a random mask, and then we will apply the mask and scale. So we are calling the function to check it how it works, and let's see, we'll run it. We can see all one shapes input, this is the input, This is the drop sample 1, this is the drop sample 2, 1, and 3, and then during the inference we can see the output is 1111, and the average over 1000 samples is 1.0045, which is exactly what it should be. It should be near to 1. So next comes custom layer using primitives. So before moving to high level keras API, we build functional layers using only tf dot variable. uh, Now we will see how to create dense layers from the primitives while mm, we building convolution 2D layer. So we'll see both use HE initialization to ensure the weights are scaled properly for ReLU activation. So let's see how it actually do. So we are defining a dense layer from primitives, fully connected layer using tf dot variable, and mathematically we have this activation function. We have defined init. We have this activation function with all the functions defined. We will do the initialization and we will use the biases if required. We will call it for the we will define call function for forward pass. We have the same function defined here, x at the rate w plus the bias, and then we will return the activation of the out, and then here we have this trainable variables, and then we have this representation. We will call this dense primitive layer function with a vector, and then we will see how does it gives the output, and this is the output that we get from the dense layer. Now we will see the convo 2D layer from primitives. So 2D convolution layer using only tf variable and tf dot nn dot con 2D. So how can we do it? We have defined this init function. We will handle the kernel size as int or tuple. Then we will select an activation function out of this, and then we will define initialization. We'll define the kernel shape with tf dot variable, and once that is done we will use the bias if required, and then we will define the call function. So in call function we will do tf dot nn dot convo 2d. This is the main logic of convo 2d, and then once the out is calculated we will add the bias to the out, and then we will pass out to the activation function. So let's test this and print the outputs. So we can see this is a convo 2D primitive. We have this input shape, we have this output shape, and we have the kernel shape. These are the total parameters that we created. So now we will have a complete CNN from the primitives. We then assemble these primitives into a complete CNN. This model proves that a complex architecture is really just a collection of basic tensors, manual weight management, and a custom dropout logic. So let's see, we have again defined here a init function with convolution layers 1 and 2, and then we will calculate the flattened size after the convolution pooling, and with the same padding and 2 cross 2 pooling twice. So this is what we are doing here. Then we will define the dense layers, and we'll call the dense layer primitive, and then we'll call the convolution block 1 with TFNN max pool 2D, and then we will define the convolution second block with again the max pool 2D function. Then we will flatten and reshape it. Once that is done, we will define the dense layers for it, and then we will return x. So this is how the trainable variables are created, and for the summary we will use this summary function where we will print the summary of the trainable parameters and whatever we have done. So let's create and test our CNN from primitives. We will test the forward pass, and then we will print the outputs. So this is our output. The last part is fourth part is custom keras layer. Now we are transitioning to proper keras layer API by subclassing keras layers layer. We get best of both worlds, custom logic and automatic weight tracking. So um, notice the structure we use build to create weight once the input shape is known and the call defined to the forward. So let's see. So here in init We have store configuration. Um, no weights yet. We don't have any weights defined. We just have units activation and the biases. We have this build function to create weights when input shape is known. So when the input shape is known, then only we will add weight and the bias, and then we will mark it as build. Uh, we have then we will call this call function for the forward pass, and then we will get the configuration for the serialization, and then we will now test the custom dense layer. We'll call it, and then we will see how does the output looks. So we have printed our configurations, what we have done here, and input output and the kernel shapes. Custom layer self attention, we use this API to build a self attention layer, the core of the transformer. We project the input into queries, keys and the values. Then we use the scaled dot product formula to determine which part of sequence are the most important. So here let's see how we do it. We have defined this class. Inside this class we have defined this init function, and with that we have defined this build function for linear projections of q, k and v. We'll define q, we'll define wk, and we will define wv. We'll add this weights, and then we will build a super we'll call super build. Once that is done, we have defined this call function where we have defined the batch size and the sequence length, and then we will do the linear projections of q, k and v. Then we will reshape for the multi-head attention, and once that is done, we will transpose the to the batch. We'll transport the q, k and v. Once that is done, we will calculate the attention score, and will apply mask if provided, and then we will do the softmax on the scores. Then we will apply attention values and reshape it back. We'll do the transpose and reshape it back and provide the output, and then we will return the output. So once the output projection is done, we will return the output. So get config is just to get the configurations. Here we are testing the class that we have defined right now, and we are printing the output. So I'll just run it. We can see the output here. The self attention layer is created, the input is printed, the output shape is printed, attention weight shape that has been created, and the transferable parameters that were created, trainable parameters that were created. Next is custom layer is spectral normalization. So this cell implements spectral normalization using custom layer wrapper. This uses power iteration to constrain the largest singular value of weight matrix, which is powerful technique for stabilizing gain training. So this is how it works, and the next topic is spectral normalization that we have already seen right now. So moving ahead on advanced architectures. So in this part we will build a modern architectural block implementing the residual block from ResNet using skip connections to let gradients bypass the deep layer. In this cell, it builds a squeeze and excitation block which acts as a channel wise attention to help the model to learn the featured importance. So if you see, we'll see the code. Here we are defining the init, main path and skip connections. um, Also we are defining a build function to, if we need to project if the dimension change, we are defining the call function. We are defining the main path, skipping the connection if required, and then we will add a activate function. So we are doing relu here. So this is how we do it, and if we call it, we can see the output. So the input and output shapes are same, and the residual block we can see, and the output shape also we can see. So this is next is the squeeze and excitation block. So in this we this squeeze and excitation block act as a multi-head act as a channel wise attention to help model to learn from the important features. So here we have this int function. We will define the build function where we'll define the dense layers, and in the call function we will do the squeeze part and the excitation part, and then we will scale it. So this is how we do squeeze and excitation in the call function for it, and then we will try to test it with some test data, and then we will print the output. So uh, the squeeze and excitation block learns which channel are important for the task and then perform accordingly. Next is the transformer encoder. So we also build full transformer encoder block. This combines layer normalization, multi-head attention, and a feed-forward network into a single reusable pre-norm component. So let's see how it is done. We have defined the init function. We have this multi-head attention. We have defined the feed-forward neural network, and we have defined the layer normalization as well. This is the dropout definition, and we are defining the call function here. So in the call function we are doing self dot layer norm 1, and attention output we are giving, and we are doing the feed forward block, and then once that is done we will return the residual connections. So to test it we are creating this transform encoder block, and then we are assigning x transformer block to y. So we will print the output. So this is the output. This is the encoder block dimension, num head, and the ff dimension, and we are printing input output shape in the parameters. Now custom training loops. While model fit is easy, manual loops give you total control. uh, we will demonstrate the basic custom training loops with gradient tape, and let's see how it works. So we have defined this custom training loops. We have defined optimizer function, optimizer as Adams optimizer, and loss function as categorical cross entropy. We have defined matrices for train loss, train accuracy, validation loss, validation accuracy, and a history to store the history. For each epoch we will reset the matrix. We will train the loop in a forward pass and then backward pass, and then we will update the weights using optimizer, and we will update the matrix also. And once that is done we will do the validation loop. For all for x batch and y batch we will validate the data that we are having. We will store prediction loss, validation loss, and validation accuracy. We will record the history, and we will print the progress, and then we will return history in the end. So this is how we have defined our class. Now we will train it with the gradient clipping. So we have this training with gradient clipping function defined here. Um this gradient clipping this adds gradient clipping to the step to prevent the exploding gradient problem from the deep network. So there is a main problem of exploding gradient in the deep network, which is prevented with the help of gradient clipping. So let's see how do we do it. We have defined this function where we have this gradient tape prediction and loss we are storing. We'll compute the gradient first with the tape dot gradient, and then we will clip the gradient by global dot norm. Once that is done we will apply the clip gradient, and then we will return the loss in the global norm. So I'll just run it. Once that is done we will go with the custom trainable module. We have hmm, if we want we can build a custom logic, but still like convenience keras we can override the train step method, and this allows us to define our own weight updated rule while using the model dot fit with all its callbacks and validations. So that's what we are doing here. And if you run this it says that custom model with trend step is defined, and we can custom model with the trend step is created, and model fit uses the custom training logic. So this is how it works. We'll move toward the next part, that is practical demo. So we'll put it all together what we have learned. Let's combine everything in a real example. We have a custom DesNet for digit classification. So we are importing the required files, we are loading the digit data set, we are setting the preprocessors, We are fitting a scalar fit, we are doing, we are reshaping for CNN, and then we are splitting the data into train, test data. Once that is done, we will print the sample, train, test, and image. We'll build a custom result model here. We will define a class. We have defined a init function. In it we have give initial convolution, residual blocks, SE block, channel attentions, and classification head. We have also defined the call function where we are defining the convolution, residual blocks, and the global pull and dropout. We are defining all these things. We will create a will create and compile now. So we have created a object of mini resnet here, and then with this resnet we will do resnet dot compile. We will pass the optimizer, the loss function, and the matrix here. Once that is done, we will build the model by calling it. So and then we will train the data on it, and then we will evaluate our data set. So I'll just run it. It will take some time to run. So this is the output. You can see we have training samples 1437, we have test samples, we have image shapes, and then we have this training epoch. Once this is done, we'll visualize the result that we have created. Okay, so the test accuracy is 98%. It is working as expected properly. Now let's visualize and see the loss curves and the model actual prediction on the test digits. So let's run it. We'll see the loss curves. This is the loss curve and this is the accuracy curve. Also we can see the predictions are 100% correct. We can see mostly all are in green. This is the advanced cheat sheet for you guys, that you can go through what we have learned, what we have used, when to use, and then all the details. So thank you so much. That's all for today.